Hi everybody, welcome back to Sea Level Physics. My name is Srinivas. I wish the grand success of each and every intermediate student, those who are appearing their intermediate exams. Okay, so today I'm going to discuss oscillations, which is very important chapter as far as mains, advanced and neat are concerned. Okay, before that, suppose there are so many kinds of motions in nature. What are they? We know very well. Earth revolves around the sun in elliptical orbit. Okay. Moon revolves around the earth in circular orbit. Okay. Similarly, seconds hand, minutes hand, hours hand moves in circular path in a clock. Am I right? Suppose in case of loaded spring, when it is pulled down and released, it makes oscillations in vertical plane. Am I right? Similarly, in case of pendulum, simple pendulum, where it is pulled aside and released, it makes oscillations. So, likewise, we can see so many kinds of motions. Am I right? So here, the motions are mainly divided into two categories. Those are nothing but periodic motions and oscillatory motions. First one, periodic or harmonic, and second one is oscillatory or vibratory. So here periodic or harmonic and second one oscillatory or vibratory. Right? What is meant by periodic or harmonic motion? See, by the name itself, periodic in the sense, the motion repeats itself at regular intervals of time in both position and phase, then that kind of motion is said to be periodic or harmonic motion. Am I right? And second one, oscillatory or vibratory, means by the name itself, oscillatory means if any motion repeats itself to and fro or back and forth at regular intervals, then that kind of motion is said to be oscillatory or vibratory. Am I right? So here see, oscillatory means here two conditions are there. Motion must be periodic as well as to and fro. So here motion must be periodic plus to and fro or back and forth. But here motion only periodic in the sense should repeats itself at regular intervals. Alright. So here motion should repeats itself at regular intervals. That's all. But here apart from that quality, here motion must be to and fro and or back and forth. Am I right? So that's why all oscillatory motions are said to be periodic, but the converse may not be true. Why? Because in case of periodic, what are the examples for periodic for one first case, that is periodic or harmonic means what are the examples? What I said now, all those said to be periodic. Suppose in case of simple pendulum, see here, this is what simple pendulum. When it is pulled aside and released, it makes oscillations to the either side of the main position. Am I right? If there is no dissipative forces, definitely time period remains same. Means it repeats at regular intervals. Why? Because there is no dissipative force, for example. So if there is no resistive force or dissipative force, so definitely it repeats itself at regular intervals. Similarly, suppose in case of loaded spring, see here, this is what spring, it is loaded like that, it is pulled aside. See, this is what main position. When it is pulled aside, suppose it pulled down and released, so then what happens? It makes oscillations to the other side of the main position, right? So here, see in this case, to and fro or back and forth here. So that's why this is what example for second one. To and fro or back and forth. Am I right? So these two are examples for exclusively oscillator or vibratory motion. Of course, these are periodic also. Why? Because here motion repeating itself at regular intervals. Now coming to few more examples. Suppose in case of revolution of moon around the earth, suppose this is what earth, moon is going to revolve around the earth in circular orbit like this. This is what moon, see, in circular orbit, for example. Here motion repeats itself regular intervals. Why? Because the time period of moon is constant. Am I right? So here periodic, but here motion is not to and fro, right? But periodic. Here to and fro as well as periodic. Here also to and fro as well as periodic. So that's why here these two kinds are periodic as well as oscillatory. But this is what only periodic. It's not oscillatory. Why? Because this is not example for to and fro or back and forth. That's why this is what only periodic. These two periodic as well as oscillatory. So what is the thing here? So all oscillatory or periodic. All oscillatory motions are said to be periodic. But converse may not be true. Means all periodics may not be oscillatory, but all oscillatory is periodic. So that's what thing here to know. So here periodic or harmonic and second one oscillatory or vibratory, right? What is the expression for vibratory or oscillatory motion? See here, what is the expression for vibratory or oscillatory? Mathematical expression. See, in case of oscillatory or vibratory, when it is displaced aside, when the particle displaced aside, what happens? Immediately some restoring force will be generated in the body or particle to bring that particle back to its initial position. That's what restoring force, right? So that restoring force is directly proportional to displacement. In fact, that is F is proportional to x power n. But here displacement as well as restoring force are directed opposite to each other. That's why minus x power n. So therefore F equal to some constant k into x power n. That is minus k into x power n. Here n is what? Some index. Takes only odd integers. That is n takes 1, 3, 5, etc. 1, 3, 5, 7, etc. Right? So here k means some constant, that is restoring force constant, n means some odd integer, x means displacement from the main position. See, this is what main position, x equal to 0. From main position here, particle is displaced on either side, right? So here, if x is positive, see, if x is positive, what happens? F is negative. Why? Because here f equals some minus k into x power n, right? Therefore, if x is positive, f is negative, and if x is negative, f is positive. See, once again, suppose I am writing here, that is f equal to oscillatory motion. What is the mathematical expression? That is f equal to minus k into x power n. N is any odd integer, that is 1, 3, 5, 7, etc. Right? So f is nothing but ma, that is minus k into x power n. Otherwise, okay. So otherwise no need to write here. That is f equal to minus k into x power n. So n takes 1, 3, 5, 7, etc. Suppose if I take least value for n, that is 1, what happens? F equal to minus k into x power 1, comma, if n equal to 3, then what happens? Minus k into x power 3, comma, if n is 5, minus k into x power 5, and so on. Am I right? And so on. See here, f equal to minus k into x power n is the simplest form for this expression. Why? Because here n equal 1, least value, that is least integer, odd integer here. So therefore n equal 1 means if n equal to 1, that form takes f equal to minus k into x. Minus k into x is nothing but simple harmonic equation. Simple harmonic equation. Right? Simple harmonic equation. What is that equation? F equal to minus k into x is the simple harmonic equation, mathematical equation or expression here. Right? Simple harmonic mathematical equation. Okay. Now, suppose if I take f as ma equal to minus k into x, that is a equal to minus k by m into x. Am I right? Ma equal to minus k into x, that is f means what? From Newton's second law, f equal to ma. That is ma equal to minus k into x, a equal to minus k by m into x. So here, if I compare with a equal to minus omega square into x, what happens? A equal to minus omega square into x. Omega square equal to k by m. Omega square equal to k by m. So omega equal to root over k by m. Here omega means what? Angular frequency. What is that? Angular frequency. Angular frequency of the oscillating particle or body. Angular frequency, right? See here, if I write like this is what? Mean position of the particle, x equal to 0. This is what? Or right side of the mean position, this is what? Left side of the mean position. During the oscillation of the particle, suppose if it moves rightwards like this, x is positive. If it moves like this, that is left side to the mean position, then x becomes negative. X becomes negative. Here x positive, here x negative. If x is positive, what happens here? See, if x is positive, f becomes minus or plus, that is minus. So minus means restoring force directed towards mean position. See, restoring force directed towards mean position. Why? Because this is the usual position of the particle when there is no oscillation. Am I right? Whenever it moves right side of the mean position, immediately restoring force develops in the body or particle to bring it back to its initial position. That's why force directed towards mean position. Am I right? Right? See here, displacement and restoring force opposite to each other, directed opposite to each other. Suppose a particle moves leftwards of the mean position like this, then x negative. If x negative means minus or plus, that is minus or plus means minus, sorry, if x is negative means minus or minus positive. So f becomes positive means f directed towards mean position like this, f. So if x negative, f positive. If x positive, f negative. So in both cases, these two, displacement and force, directed opposite to each other. See here, what is the direction of acceleration? The direction of acceleration also same as that of the direction of force. So here, acceleration also directed like this. Here also acceleration directed like this. So why? Because force and accelerations are parallel to each other. Am I right? Okay. Now, during oscillation, a particle reaches extreme position to here, means velocity gradually decreases. Why? Because it is moving opposite to the restoring force. Definitely, when it moves from mean position to any side, what happens? Its speed gradually decreases. Why? Because suppose your particle moves rightwards, what happens? It is moving against force. Therefore, it is under retardation. So gradually its speed gradually decreases and becomes 0 here at extreme position. What is extreme position here? X equal to plus a. Right side x equal to plus a. Here x equal to minus a. Am I right? So from mean position, as it moves right side, what happens? Speed decreases and becomes 0 here at extreme position. The speed is 0, kinetic energy also 0 at extreme position. Kinetic energy 0. Right? Potential energy maximum. Potential energy is maximum. Here also see, when it moves left side of the main position, that is, it is acted upon by restoring force once again. So this is under retardation once again. So retardation in the sense again speed decreases and becomes 0 at extreme position, right? If speed is 0, kinetic energy also 0, potential energy maximum, PE becomes maximum, right? So at extreme position, post extreme position, speed 0, kinetic energy 0, potential energy maximum. In the same way, at the negative extreme position, speed 0, kinetic energy 0, potential energy maximum, right? Okay. If x equal to 0, what happens? That is when particle reaches mean position instantaneously. Then what happens? If x is 0, force 0. So see here, we know that f equal to minus kx. First option, if x positive, what happens? F equal to minus into plus, that is negative. If second option, if x negative, then what happens? F equal to minus of minus, minus of minus, minus of minus, that is positive, right? If x equal to 0, if x equal to 0, force also 0, that is force also 0, acceleration also 0, right? Okay. Similarly, if x equal to 0, what about acceleration? Acceleration 0, force also 0. If x equal to plus a, for example, if x equal to plus a, that is when it reaches positive extreme position, then what happens? F equal to minus Ka, minus K into plus A, that is minus Ka. Regarding acceleration, A equal to minus omega square into A, right? Acceleration equal to A equal to minus omega square into A. If fifth point, if x equal to minus A, then what about acceleration? A equal to minus omega square into minus A, that is plus omega square into A. So A equal to minus omega square into minus A, that is plus omega square into A, plus omega square into A. So if you observe carefully, here acceleration is not uniform. Why? Because during oscillation, when it reaches mean position, acceleration 0, restoring force 0, acceleration 0. But when it moves away from the main position, acceleration increases either side and becomes maximum at the extreme position. See, when x equal to plus or minus a, acceleration becomes maximum. Acceleration becomes maximum. Here also maximum, right? So acceleration is not uniform. Why? Because this is position dependent. Acceleration is position dependent, right? Right. Acceleration is position dependent. Next one, harmonic function. What is meant by harmonic function? If any function repeats itself at regular intervals, similar to periodic motion, that periodic motion can be represented by one mathematical expression. That expression itself, periodical function. Okay, periodic harmonic function. Periodic harmonic function. What is meant by periodic harmonic function? If any function repeats itself at regular intervals, then it is said to be periodic function. Suppose f of theta is one function, mathematical function. If it repeats at each interval, time interval, equal time intervals, then f of theta plus t becomes equal to f of theta. See, initially this is what f of theta. In next to t times, again f of theta plus t becomes equal to f of theta. Means that is periodically changing. See, periodically repeating once again. So that's why if f of theta plus t equal to f of theta, then that function is said to be periodic harmonic function. Similarly, sine function. if we consider sine and cosine functions, for example, sine of theta plus, suppose t is replaced by some angle 2 pi. Why? Because t means time period. Within a time period, what is the phase angle acquired here? 2 pi. That is sine theta plus 2 pi equal to sine of, what happens? Sine theta plus 2 pi. Again sine theta, right? Similarly, cosine. Cosine theta plus 2 pi. That is cos theta plus 2 pi equal again cos theta. Means in every 2 pi angle, that function repeating, both the sine and cosine functions repeating at regular intervals. That's why these are said to be periodic harmonic functions. Periodic harmonic functions. See here, f of theta can be written as sine theta, otherwise f of theta can be written as cos theta. So therefore, f of theta equal to sine theta. Similarly, f of theta can be written as cos theta. Am I right? F of theta equal sine theta, otherwise f of theta equal cos theta. Right? If I replace theta by time, that is, if theta equal to t, then f of t can be written as sine theta. Sine theta means, what is theta here? Theta means omega t. We know that theta equal to omega t, that is sine omega t. Sine omega t. Theta means omega t. Again sine omega means 2 pi by capital T into small t. Right? Here also, if theta equal to is replaced by t, then f of t equal to cos theta, that is cos theta means again omega t equal to cos 2 pi by capital T into small. So these are nothing but simple harmonic functions. Simple harmonic functions. So any function repeats itself and expressed by either sine function, otherwise cosine function, then those functions are said to be simple harmonic functions. Okay, simple harmonic functions. One more point, that is, so what are simple harmonic functions? Simple harmonic functions. What are simple harmonic functions? That is f of t equal to sine 2 pi by capital T into small t. Similarly, f of t equal to cos 2 pi by capital T into small t, and combination of both. What is that? F of t equal to a sine 2 pi by capital T plus a sine 2 pi by capital T into t plus b cos 2 pi by capital T into t, like this. See here, these are said to be simple harmonic functions. What are the simple harmonic functions here? F of t equal to sine 2 pi by capital T into small t. Similarly, cos 2 pi by capital T into small t, and third one, combination of sine and cosine functions. So these are said to be simple harmonic functions. Am I right? Next one. Suppose if any function repeats itself at regular intervals, then it need not be simple harmonic. Why? Because here, suppose one example. See one example here. This is what f of t for function repeats at regular intervals. See here, this is what time at t. In next t, once again repeating 2t. In next t also repeating, that is 3t. Next t also repeating, that is 4t, like, and so on. See, if you observe this function, some function f of t repeating itself at regular intervals like this. Am I right? But here see, if you observe, this variation cannot be expressed either by sine or cosine. Why? Because what is sine function here? Sine function we know very well, that is f of t equal to sine 2 pi by sine omega t, that is sine 2 pi by capital T into small t versus time. What is the variation here? Like this. positive and negative cycles like plus minus like. See, when t equal to 0, 0, it takes value 0. When t equal to p by 2, again p equal to t by 2 means what is the angle in terms of angle pi? Here 0. Here what is the time here? Somewhere here that is 3t by 4. 3t by 4. Here 2 pi. Right? 2 pi means time period. So this is the variation of sine function with the time. But here it's not sine ideally varying or cosine ideally varying. That's why even though it is periodic, it cannot be harmonic. It cannot be harmonic. So this kind of function periodic only, periodic, but not simple harmonic or harmonic, but not harmonic. But not harmonic. So even though it is periodic, why it is periodic? It is repeating itself at regular intervals. That's why periodic, but it cannot be expressed by either by sine function or cosine function. That's why it's not harmonic. Am I right? So simple harmonic motion can be expressed either by sine function or cosine function or combination of both. Right? Now what about the tan or cot? Means tan or cot, they are not repeating in regular intervals. Suppose tan theta. If we take tan theta that is f of t equal to tan theta, that is a tan. What is a tan theta? For theta 0, if theta equal to 0, tan 0, what is a tan 0? 0. Tan 0 equal to 0. Tan 90 equal to infinite. Similarly, f of t equal to cot theta. F of t equal to cot theta. So cot theta means cot 0 equal to 0. But cot 1 by 0 means infinite. Cot pi by 2, that is 1 by infinite 0. Right? Okay. So it is increasing from 0 to infinite, not repeating. Here also it is decreasing from infinite to 0. So not repeating at regular intervals. So that's why they cannot be simple harmonic. So simple harmonic functions in the sense they must be represented either by sine or cosine functions and must be repeated at regular intervals. So based on these points, let us see some examples. Right? The first example. See, example 1. F of t equal to sine omega t plus cos omega t. This is the given function. F of t equal to sine omega t plus cos omega t. So this is the combination of sine and cosine. Is it harmonic or not? If it is harmonic, what is the form of that harmonic function? If I extend like this, see, it is multiplied and divided by root 2. Suppose it is multiplied by root 2 like this. Sine root 2 of sine omega t plus cos omega t whole divided by root 2. So root 2 by root 2 neutralize. You will get above step 1. So nothing will wrong by doing like this. So multiply and divide by root 2 here. Then root 2 into, I'm splitting sine omega t into 1 by root 2 plus cos omega t into 1 by root 2. Right? So that is root 2 times sine omega t. What is 1 by root 2? Try to take the form sine a cos b plus cos a sine b. So as it is sine omega t, replace 1 by root 2 by writing cos pi by 4. So sine a cos b plus cos a sine b form. So cos omega t into 1 by root 2. Replace 1 by root 2 by writing sine pi by 4. So sine a cos b plus cos a sine b. So on extending like that, sine a cos b plus cos a sine b means sine of a plus b. Sine of a plus b like this. Sine of a plus b See this form. Suppose f of t is replaced by some displacement. Say f of t equal to some displacement y. Say like this. Say like this. So for some vibrating particle, if this is the mathematical expression, the variation of displacement with the time, like this. See, f of t is replaced by some displacement y for any vibrating particle. So what is the mathematical expression here for the displacement? Y equal root 2 times sin omega t plus pi by 4, right? Sin omega t plus pi by 4. How to write this form? Variation. Suppose if I take t equal 0, y at t equal 0 means initial displacement. When t equal 0, what is the displacement of the particle? That is 0 plus pi by 4. That is root 2 into sin pi by 4. Root 2 into sin pi by 4. That is root 2 into 1 by root 2. Like this. Root 2 into, see, t equal 0, sin pi by 4. 1 by root 2. Root 2 times 1 by root 2. That is 1. That is 1. Am I right? So what is the displacement here? Initial displacement 1 means graph not starting from the origin. So by the time when t equal 0, it possesses some initial displacement. So variation can be written like this. Variation can be written like this. See, when t equal 0, we have some initial displacement. Alright, that is like this. So graph not starting from the origin. Am I right? See, this what displacement. Otherwise, f of t equal to displacement, for example, versus time. So when t equals 0, what is the displacement here from here to there? That is 1 meter. In SI system, suppose if it is in SI system, this is what? 1 meter. Right? What is the initial phase? When t equals 0, this term is said to be phase. Phase. So sin of omega t plus pi by 4 is said to be phase. When t equals 0, we left with pi by 4. So this, if I extend like this, so it would start from this position. So this corresponds to pi by 4. See, t equals 0. By the time when t equals 0 already has some phase angle. This corresponds to, suppose here if I extend by some dots, it strikes the time axis somewhere here. So this intersection is nothing but initial phase, that is pi by 4. Pi by 4 initial phase. Now this height is nothing but initial displacement. So variation of displacement versus time can be shown like this for this expression. Am I right? For this expression. And next one, coming to next one. F of t equal to example 2, f of t equal to sin omega t plus cos 2 omega t plus sin 4 omega t. See, this is the combination of sine function, cosine function, and again sine function, but with different angular frequencies or time periods. Coming to this one, what is the angular frequency here? Omega. So omega can be written as 2 pi by t, or t equal 2 pi by omega. So what is the time period for this expression sin omega t? That is 2 pi by omega. Means within every 2 pi by omega time, the function will be repeated. That is the meaning. So in every 2 pi by omega, function sin omega t is repeating itself. Similarly, for cos 2 omega t, means here, what is the multiple for t here? 2 omega. So 2 omega can be written as a 2 pi by some t dash, for example. 2 pi by t dash. Now t dash equal to t dash can be written as a 2 pi by 2 omega. That is 2 pi by omega by 2. That is t dash equal t by 2. Now whatever the 2 pi by omega here, 2 pi by omega means t in case of sine function, sine omega t function. So t by 2 can be written as 2 by 2. So what is the time period for the second expression, that is t by 2, half of the previous one. For this one, t equal 2 pi by omega. For this one, t dash equal 2 pi by omega by 2. That is half of the previous time period. Coming to third function, that is 4 omega t. That is 4 omega. What is the multiple for t here? 4 omega. Can be written as 2 pi by t double dash, for example. So t double dash means time period for exclusively time period for this function. That is t double dash can be written as 2 pi by 4 omega. That is 2 pi by omega whole divided by 4. Now 2 pi by omega means capital T. That is the time period for first function. That is in terms of this one, t double dash can be written as t by 4. T by 4. See here, this one, for this one time period t. If time period of first function is t, for second function that is half of t, and third function that is 1/4 of previous one, like this. Okay. Now coming to e power exponential functions cannot be simple harmonic. See, this is what simple harmonic. Even though this is combination of sine, cosine, and again sine, ultimately the combination can be written as simple harmonic, but with different time periods here. Okay. Now, example 3. Third example. F of t equal to e power minus omega t. Exponential function. E power minus omega t. Exponential. Is it simple harmonic or not? See here. At t equal to 0. At t equal to 0. What about f of t? F of t equal to e power 0. That is 1. At t equal to infinite, f of t can be written as e power minus infinite. T equal to infinite, e power minus infinite. That is 1 by e power infinite. That is 1 by infinite. That is 0. That is 0. So the value decreasing from 1 to 0 exponentially, like this. Exponentially. At t equal to 0, what is the value of function here? At t equal to 0, 1. At t equal to infinity, it reaches to 0, like this. Exponential variation. Right? Okay. And fourth one, example 4, logarithms. Log of omega t. Log of omega t. What about log of omega t? F of t equal to log of omega t. F of t equal to log of omega t. At t equal to 0, f of t can be written as log 0, that is 0. At t equal to t tends to infinite, log of infinite, that is f of t tends to infinite. So here also the value of function increases from 0 to infinite, not repeating. So that's why it's not periodic, it's not harmonic, right? So therefore variation is like this. So f of t versus time, so increasing like this. Okay, so these functions cannot be simple harmonic. So that's about some examples for simple harmonic and non-simple harmonic functions. Okay friends, in next video we will discuss exclusively simple harmonic motions. Okay, thank you friends.